Hello everyone, welcome to General Chemistry 1. Today our focus will be on solutions. We'll review a little bit about concentration, especially molarity, and then we'll move on to colligative property and osmosis. The concentration, there's many different ways to calculate concentrations. As some of you might already know, the percent concentration is the mass or the volume of solute. If the mass will be in gram, volume will be in milliliters. Divided by the mass of solutions in gram or milliliters, and you can mismatch them. Okay. Now and multiply it by 100. So that's pretty simple. It's the components, the active ingredient divided by the whole solution times 100, and that gives you a percentage. And you can mismatch, like I said, you can do mass over mass, mass over volume, or volume over volume. Okay, volume is for liquid, mass is obviously for solid. Okay. And solution you can have all solid as well, like brass is solid copper and zinc mixed together, melt and mix together and then become a solid brass. So solution doesn't have to be liquid or gas. Okay, it can be solid as well. All right, remember the mass of solutions is mass of solute plus mass of solvent. And in most cases, when you add the volume of two substances together, you should come up with the same, as total. So the total volume is the volume of solute plus volume of solvent. In most cases, sometimes there's interactions that reduce the volume or increase the volume a little bit. Okay, it's good to know the part per million and also part per billion. Million is 10 to the 6 and billion is 10 to the 9. So the percent is part per 100, and that's what the percent means. So you can do just like you do percentage, the solute divided by solutions, and you multiply it by 10 to the 6 for part per million and 10 to the 9 for part per billions. Okay, and here's the important one, the two important concentrations, the molarity and molality. Most of us probably already know molarity as well. It's the number of moles of solute divided by the volume of solutions. Units has to be in liters. If most of the time we will be given grams of the solute, and we need to be able to convert gram to mole. And hopefully you remember, from gram to mole, you divide it by molar mass. Okay, you should know what the substance is. For example, sodium chloride, molar mass is 58.44. You take sodium plus chloride. Okay, and then so you take the mass divided by molar mass, you get yourself number of moles. And if you're given the volume in milliliter, you divide it by thousands, because there's 1,000 mil in a liter. Divided by 1,000 will convert milliliters to liters. Okay. Molality is very similar. It's instead of divided by volume of solution, here you divide it by the mass of solvent in kilograms. Okay, so mole of solute divided by mass of solvent in kilograms. Ion concentrations. It's important to know how many ions are in the solution. So here's a very good example. When you have sodium phosphate, you have 3 sodium ion plus 1 phosphate ion. So that have 4 ions total. Okay, and that's the number of ions is also known as lowercase I, the Van Hoff factors. So in this case, if we have 1.5 molarity of sodium phosphate, the total would be 3 times of that for sodium, make it a 4.5, and 1 time of phosphate is the same, 1.5. So 4.5 and a 1.5, so you have a total of 6 molarity for ions. Okay, so every 1 sodium phosphate, you have 4 times. Okay, because you have 3 sodium and 1 phosphate. Let's make it 4. And for dilutions is M1 times V1 equal to M2 times V2. M1 V1 is molarity before and volume before. M2 is molarity after, and V2 is the volume after. Like when you make the solution more diluted, or you make solution less diluted by evaporations. When you add more water to the solutions, it becomes more diluted and the concentration will decrease. If you evaporate the solutions, you get rid of the water or the solvent. The volume goes down, so the concentration goes up, become more concentrated. Okay. It works for molarity, also works for concentration, so that's percentage or ppm, ppb as well. Now the molality is really important because we need that to calculate the colligative properties, which means every time you add a solute into a solvent, you will change the boiling point and also the freezing point and osmotic pressure. Okay. For freezing point, the difference in freezing point is called freezing point depression because the freezing point will go down. For example, water, the freezing point is 0 degrees Celsius. When you add in a solute, it will decrease the freezing point, which means it will freeze at lower temperature. Okay, so delta T will be M, which is molality, multiplied by a fixed number, constant K. For water, it's 1.6 degree per molality. Now, on the other hand, your boiling point will be increased, and that's what we call boiling point elevations, go up. Okay, and delta T, how much up? It will be M multiplied by Kb, which is for water is 0.5. So it's not much per molar. Okay, it's not much. So it decreases more than it increases. All right. So that's called colligative property, and also it affects the osmotic pressure as well. And what is osmotic pressure? Okay. First of all, what is osmosis, right? I have a nice picture here in the textbook. If you have a tube like this with a divider called semi-permeable membranes, these membranes only allow the solvent. Notice that pure solvent, for example, water. Ethanol is also a pure solvent. So water is just very popular. So those gold molecules are water. Imagine that, okay? Now, it's only allow water to move freely because relative to the solute is smaller, okay? So that's the design of the membranes. It's for those of you who are curious what the membranes look like, it's like a microwave saran wrap, okay, the microwave wrap. It's nice and crystal clear. It's pretty nice. It has tiny hole that allow water to pass through, but not the ion, not the sodium, okay, not the chloride ion, for example. So, but anyway, if you have a divider like that, and one side you have a solution with solutes, so you don't have that many solvent molecules. On the other side, you have pure solvent. Okay, so naturally, it will push the solvent to the right side. Okay, and it's like diffusions, because to balance it out, because you don't have a lot of solvent on the right side, you have a lot of solvent on the left side. Now, either the solute will move or the solvent will move, but the solute are not allowed to move. Okay, so you can only move. So that's the natural push, and that's called the pressure. Okay, that pressure that push all this guy to the right side. All right, now if you apply exactly the same pressure, then you will stop the movement. Okay, so if you apply the pressure, okay, and it's called osmotic pressure. So that's the pressure that move the solvent, okay, across the semi-permeable membranes, and that's because of the solutions. Okay, if both sides have the same concentrations, then there's no movement. And here, obviously, on the left side, you have zero concentration of solute. On the right side, you have some solute. Okay, so there's a difference in concentrations. Therefore, there's a movement. It's always go from low concentration of solute to higher concentration of solute. Now, the arrow here is mean that you push it back. Okay, that's when you push it. When you apply a pressure and there's no movement, you know that pressure is the same as osmotic pressure. It's just opposite directions. Okay. All right. So that's osmotic pressure. And so osmosis is the process in which solvent molecules pass through a semi-permeable membrane that only allow the solvent. Okay. And as I mentioned earlier, osmosis occur due to the difference in concentration of solute or as a solvent. Okay. So osmotic pressure is the pressure that pushes the solvent. So if you want to stop it, you need that pressure to prevent the flow. Okay, and that's called osmotic pressure. And so we have the formula for that. Osmotic pressure is, and we'll do a practice on that, is equal to I, which is Van Hoff factor multiplied by M, molarity, and R, time, and T. Okay, R is the gas constant, 0.08206, and T is temperature in Kelvin, obviously. Okay, so we'll do some calculation on those, and here's are some of the practice questions, and in the next video we'll go with them. So that's the key concept. Maybe we'll miss a couple things like effect of vapor pressure, things like that. Vapor pressure. Okay, so that's maybe one other thing. We can discuss that in the next video. Okay, and that's also known as Raoult's law. All right, guys, thank you for watching, and in the next video we'll wrap up some more topic, and then we'll go into the sample. Okay, some calculations. Should be fun stuff. Thank you for watching.